Okay. हाँ. Okay, so let's start the today's session. In the last session, we have taken one problem based on the first law of thermodynamics for a closed system, right? In the last lecture, we have taken one problem, okay, and it has combined three processes. Okay, so let's take one more problem based on this. Okay, so you'll be in a position to understand this first law of thermodynamics for a closed system in a better way. Okay, so let's start. Okay, so 60 liters of an ideal gas, 60 liters of an ideal gas at 290 Kelvin, and 1 bar, is compressed adiabatically, to 10 bar. It is then cooled at constant volume. It is then cooled at a constant volume and further expanded isothermally, so as to reach condition from where it started. Evaluate first pressure at the end of constant volume cooling. Second, change in internal energy. During constant volume process. Third, net work done and heat transfer during cycle. Assume Cp is equal to 14.25 kilojoule per kg Kelvin. Cv is equal to 10.25 kilojoule per kg Kelvin. Okay, so this is the problem. Okay, you find the problem to be very lengthy. Okay, but I will tell you the solution is very simple. Okay, so see, let's go by each and every sentence. Okay, let's start with each and every sentence. What I say? 60 liters of an ideal gas. Okay, 60 liters. It is nothing but a volume, right? Liter is nothing but a volume. Okay, so this is nothing but initial volume. So V1 is 60 liters. Okay, so how will convert liters into meter cube? By multiplying by 10 raised to power minus 3. Okay, so this becomes in meter cube, right? 60 into 10 raised to power minus 3 meter cube. Okay, so this is your volume, right? 60 liters of an ideal gas. See, 60 liter is a volume. So when you multiply it by -3, it becomes in meter cube. So 60 liters of an ideal gas, right? So they have mentioned it as an ideal gas. So basically, you should know the value of Cp, Cv, okay, of ideal gas. See, if they mention that 60 liters of an air, so for air, we know the value. Cp is 1.005, Cv is 0.718, R is 0.287. So those values we remember. But they have mentioned it as an ideal gas, and for which they have already given the value of Cp and Cv. Cp and Cv is already given, so it doesn't matter, right? At 290 Kelvin. So this is nothing but temperature. So T1 is 290 Kelvin. Okay. And 1 bar. So obviously it will be a pressure. So P1 is equal to 1 bar. Okay. So as I explained you in the last lecture, when you multiply this bar by 100, it becomes in kilopascal. So I will write down, these are the 100 kilopascal. Okay, bar, how to convert bar into kilopascal? Multiplied by 100. So it becomes in kilopascal. Is compressed adiabatically. Okay, so let us start drawing the diagram. Okay, so let this be the pressure scale. Let this be a pressure scale. Let this be a volume scale. PV diagram we will start. Okay, so we are at basically this point. We are at this point number 1. Okay, so this is our point number 1. Okay, so from this point number 1, basically, okay, see 60 liters of an ideal gas at 290 Kelvin and 1 bar. Okay, so see, if I need to plot, okay, so at point number 1, okay, I'll just plot it. At point number 1, what is the pressure? P1 is equal to 100 kilopascal. Try to understand. Pressure here is at point number 1, pressure is 100 kilopascal. What is the volume? Okay, V1 you will get it here. So V1 I will just write down these as 60 into 10 raised to power minus 3. Okay, 60 into 10 raised to power minus 3. So how we used to write down? 0.060, right? Meter cube. 0.06 meter cube, right? So this is nothing but 60. So I'll just write down here 0.060 meter cube, right? So this is our volume scale, 0.060 meter, right? So this is P1, this is V1, right? So 60 liters of an ideal gas, this is nothing but a volume at 290 Kelvin and 1 bar. So 1 bar is a pressure. Okay, is compressed adiabatically. Okay, so from this point number 1, we need to compress it. And how we should compress? We should compress it adiabatically. Okay, so see, whenever there is a compression, pressure will increase, volume will decrease. Okay, so what I'll do, I'll just plot this process like this. Okay, so let's see that we have reached to point number 2 here. Okay, so we have reached point number 2, right? We have reached point number 2. Okay, so this 1 to 2, it is nothing but what? 1 to 2, it is nothing but a compression. You can see from 1 to 2, pressure got increased, volume got decreased. Okay, so we have reached to point number 2. Okay, so it is compressed adiabatically to what? 10 bar. Okay, so here what I want the pressure P2. Try to understand. So I want pressure to be equal to 10 bar. So 10 bar. Okay, 10 into 10. Okay, so that will do 10 into 100. Sorry, so we'll get it. This has 1000 kilopascal. Okay, so P2 here it is nothing but 1000 kilopascal, right? So this is a pressure what we want at point number 2. See, it is compressed adiabatically to 10 bar. So from here we will compress it. Okay, we'll compress it to what? 10 bar. So 10 bar, it is nothing but 100 kilopascal. Okay, so now we are reached to point number 2. Okay, but you should mention here this process is adiabatic. So we should mention the law of PV raised to power gamma is equal to C. PV raised to power gamma is equal to C. Right? This law I mentioned is compressed adiabatically to 10 bar. It is then cooled at a constant volume. Try to understand. After that, what we need to do? We need to cool it. But during cooling, volume should remain constant. Okay. So see, constant volume, it's nothing but a vertical line. See, we need to cool it at a constant volume. So constant volume, it is nothing but a vertical line. When on the vertical line, if you move upward, okay, if you move upward, it is heating. But when you move downward, it's a cooling. Okay, so from point number 2, I will start moving downward. Okay, so I will start moving downward so that I will reach point number 3. Try to understand. See, I'll repeat. Once you reach it to point number 2, it is then cooled at a constant volume. So from point number 2, I will start cooling. Okay, that means I will reach the point number 3. But what happens during 2 to 3? Okay, volume is to be kept constant because it is mentioned in the problem. Okay, so I want the value of V3 to be equal to V2. Try to understand. See, it is then cooled at a constant volume. So from point number 2 to 3, volume remains constant. At the same time, it gets cooled. It gets cooled. Okay. Now what happens from point number 2? If you move upward, okay. See, from point number 2 at constant volume, you have two possibilities. Either you move upward or you move downward. If you move upward, it's a heating. If you move downward, it's a cooling. Right. So that is the thing which I've done. I moved downward. It's a cooling. So it moves at, see, it is then cooled at a constant volume. And after, once you reach it to point number 3, what they have done, see, okay, what they have done. Okay, see, let me write down this. So V2 is equal to V3. Okay, so once you cooled at a constant volume, further expanded isothermally so as to reach the condition from where it is started. Okay, so from point number 3, we need to expand, but how? Isothermally. Okay, so see, this is compression. Now we need to expand it. But that expansion should be isothermal. Okay, so what I'll do? So from point number 3, I will start expanding, but till what I should expand? So as to reach the condition from where it is started. So from 1 it is started. So if I need to start expanding from point number 3, I need to expand it to point number 1 because it is mentioned in the problem. It is expanded isothermally so as to reach the condition from where it is started. So from this point number 3, you start expanding, but till what you will expand? Okay, till the point from where it is started. So obviously it has started from point number 1, right? So what we'll do? Okay, I will just start connecting point number 3 to point number 1. Okay, so this is how it will expand. Okay, so from point number 3, I will move, okay, to point number 1. But how I should move? I should move in such a manner that it will get expanded isothermally. So for isothermal expansion or for isothermal process, what is the law? PV is equal to C. For isothermal process, PV is equal to C, right? And what is the meaning of isothermal process? The meaning of isothermal process is, okay, the temperature at point number 3, it should be equal to temperature at point number 1. See, from 3 you start expanding isothermally till you reach point number 1. So 3 to 1 is an isothermal process which is governed by law PV is equal to C. Okay, so what do you mean by isothermal? Temperature at point number 3 is equal to temperature at point number 1. Okay, now what they're asking, evaluate the pressure at the end of constant volume cooling. Okay, so constant volume cooling is 2 to 3. Okay, so 2 to 3, it's a constant volume cooling. Okay, and they're asking what is the pressure at the end. Okay, so what they're interested to calculate what is the value of P3. Pressure at the end of constant volume cooling. So from point number 2, the constant volume cooling will start, and at point number 3, the constant volume cooling will end. So they're asking what is the pressure at point number 3. Okay, you can see pressure at the end of constant volume cooling. So 3 is the end of constant volume cooling. So they're asking P3. Change in internal energy during constant volume process. So 2 to 3 is a constant volume process. So change in internal energy, obviously it is internal energy at the final state. Okay, that is at point number 3 minus internal energy at the initial state, that is U2. Okay, so change in internal energy, you can see change in internal energy during constant volume process. So what is the change in internal energy during constant volume process? That is 2 to 3. How will you calculate? Internal energy at the final state minus internal energy at the initial state. Similar to what I am asking. Third, net work done at and heat transfer during the cycle. So they're asking what is the value of Q1, 2, 3, 1. Similarly, they're asking the value of what is the value of W1, 2, 3, and 1. Right? They're asking this. Okay. See, net work done and heat transfer during the cycle. So see, 1, 2, 3, back to 1 is a cycle. So we are interested to calculate heat transfer and work transfer during the cycle. Have you understood the given data? Let me know. Have you understood? Have you understood given data? Have you understood or not? Okay. Is that okay? The given data is okay or not?
Understood, sir.
Okay, okay. Now let us start. Let's start. See, let us start. Now see, if we need to solve such sort of problem or any problem, you should know pressure, volume, and temperature at every point. Okay, you should calculate pressure, volume, and temperature at every point. Right? Okay, you can see now. See, Cp is given, Cv is given, right? See, you can see at point number 1, pressure is known, volume is known, temperature is known. You can see P1, V1, T1 is known. Okay, let us start with this. See, Cp is this, Cv is this. Okay, we should know the R. Okay, how we used to calculate R? R, it is given by difference between Cp and Cv. See, this you already know. We have taken the derivation. Difference between Cp and Cv is R, right? So just calculate it. So it is 14.25 is Cp minus Cv is 10.25. Okay, so we'll get that value as 4.25, 4, right? We'll get this value as 4 kilojoule per kg Kelvin, right? We'll get that value as 4 kilojoule per kg Kelvin, right? This value is 4. Try to understand, right? This is 4 kilojoule per kg Kelvin, right? So this is how we calculate R. Similarly, we should calculate gamma. Okay, why we are calculating that you will know now. It is basically the ratio of Cp by Cv. Okay, so Cp is 4.25, Cv is 10.25. So just calculate this value, Cp by Cv, 14.25 divided by 10.25. 14.25 divided by 10.25. Just do this. Let me know immediately what answer we are getting. Let us do that. Can you do this or not? 14.25 divided by 10. Do it. Okay. Each of you should practice this. 14.25 by 10. We are getting this as 1.425, right? 1.425. Right? So this is 1.425. Right? So this is what we got, gamma, right? Now see, now let us start. See why I have calculated this first, because it is required. It is required. Value of R should be known, value of gamma should be known. You can see here, gamma is required. How I calculated gamma? Cp by Cv. Now R, it is why I calculated R, because you know this ideal gas equation that is given by PV is equal to MRT, right? This ideal gas equation we can apply at any stage. Now I will apply it for state number 1. So P1 V1 is equal to MRT1. Try to understand. P1 V1 is equal to MRT1. I have applied it for state 1. The reason behind this is, see, this pressure is known. Try to understand. This pressure is known. Volume is known. Okay, R is known. Temperature is known. I can calculate mass. Okay? See, why I applied at state number 1? P1 is known, V1 is known, T1 is known, right? R is known. So I can calculate mass now. Okay, so I'll just put that P1 is 100 into V1. V1 is 0.060 is equal to mass into R. See, that is the reason why I calculated R. R is Cp minus Cv. So this is 4 into T1. Into T1, you can check it. It's 0 T1. It's 290, right? T1 is 290. Okay, T1 is 290. So just do the calculation and just get the value of mass. Just do the calculation and just get the value of mass. Okay, so let's see what value of mass we are getting. Let us see what value of mass we are getting. Okay, so can you calculate this value? Let me know. Can you calculate this value? What value of mass you got? What value of mass you got? Can you tell me what value of mass we got? See, all of you must do these calculations. Huh? See how much, what value of mass you got, all of you. Can you do this calculation? Let me know immediately. Okay, let us calculate it as 100 into 0.060. Let this add gets closed. Okay, 100 into 0.060 upon 4 into 290. Okay, you got this value of mass 0.0052. I will take kg. Okay, you can check it. Is that okay? All of you, is that okay? Let me know. Is that okay?
Yes,
Is that okay
sir.
or not? Yes. Now let us start. Let us start. See, all the properties at point number 1 are known. All the pressure is known, volume is known, temperature is known. Now we need to calculate the properties at point number 2. Okay. Now see, in order to calculate those property, okay, we have seen this relation. We have seen the relationship between temperature, pressure, and volume. See, this process 1 to 2, it's a adiabatic process. You can check it. Process 1 to 2. Okay, it's basically the adiabatic process, right? Process 1 to 2, it's a adiabatic process. So for adiabatic process, okay, we have seen the relation T2 by T1 is equal to, okay, P2 by P1 raised to power gamma minus 1 by gamma is equal to V1 by V2 raised to power gamma minus 1. Okay, you can check it. This expression we have already derived. This is a relationship between temperature, pressure, and volume for adiabatic process. Why I have taken this relation? Because 1 to 2 is an adiabatic process. So this is a relation which I have written. Okay, right? Now see, I'm interested to get the value of T2. Similarly, I should know P2. Similarly, I should know V2. Okay. So T2, P2, and V2 I should know. So for that, okay, what I will do, initially I will equate these two terms. Okay. So when I equate these two, what value of T2 I will get? T2 is equal to T1 into P2 by P1 raised to power gamma minus 1 by gamma. Check it. You'll get this value. Okay. So from this, we will calculate T2. So T2 is given by T1. Value of T1, it is given in the problem, 290 multiplied by P2. P2 is 1000. Okay, you can check it. P2 is 1000 upon P1. P1 is 100. 100 raised to power gamma. Just now we have calculated gamma. Okay, so this is 1.4. Okay, 1.425 minus 1 upon 1.425, right? Upon 1.425. Okay, so from this we'll calculate T2. Let's calculate the value of T2. Okay, just do the calculation and let me know. T2. Do this calculation fast. Okay, let's do this calculation. So what we will get? 290 into, okay, 1000 by 100. Okay, raised to power 1.425 minus 1 upon 1.425. Okay, you can check what temperature we are getting. We are getting this as 576.29. 576.29, right? So this is the value of temperature what we got, right? This is the value of temperature what we got. 576.29, right? So this we got it as temperature at point number 2, right? This we got it as temperature at point number 2. Okay, let us calculate similarly. Let us calculate the similarly. Okay, pressure. Similarly, we can calculate pressure at point number 2. Okay. See, pressure at point number 2 is given. V1 is, see, T2 we have calculated. See, in this equation, T1 is known, P2 is known, P1 is known. So we have got T2. Okay. Similarly, if we equate these two, if we equate these two, V2 we can calculate, right? V2 we can calculate. So let's do that. Okay. So see, if you equate these two, so if you equate these two, what you will get? You will get these as P2 by P1. See, gamma minus 1 gets cancelled. What is the meaning? P2 by P1 raised to power 1 by gamma is equal to V1 by V2 is equal to V1 by V2. P2 by P1 raised to power 1 by gamma is equal to V1 by V2, right? Now we are interested to get the value of V2, right? What do we want? We want the value of V2. So how we will calculate that value? How will calculate the value of V2? Okay, so just reverse it. Okay, so this becomes P1 by P2 raised to power 1 by gamma is equal to V2 by V1. Just reverse it. So P1 by P2 raised to power 1 by gamma is equal to V2 by V1. So V2 is given by, I will write down, V2 is equal to V1 into P1 by P2 raised to power 1 by gamma, raised to power 1 by gamma. Let's put the values now. V1, it is mentioned in the problem. You can check it. It is 0.060. Okay, this is 0.060. P1 by P2. P1 is 100. Okay, P2 is 1000. Raised to power 1 by gamma is 1.1425. 1.425. Okay, so from this we will get the value of V2. Okay, so from this we will get the value of V2. So let's calculate that value. Let us calculate that value.
0.011.
0.011. Okay. Okay, no problem. Okay. So see, it's a volume, right? Volume will be in meter cube. See, unit of V2 will depends upon unit of V1. See, unit of V2 will depends upon unit of V1 because P1 and P2, okay, they have same unit. It will be get cancelled. Gamma will not have any unit. So unit of V2 will depends upon unit of V1. So we are getting this as meter cube, 0.011 meter, right? Now see, okay, see, now we know, see, P2 is known, right? P2 is known. T2 we have calculated. Also V2 we have calculated, right? P2 they have mentioned in the problem. T2 we have calculated. Again V2 we have calculated. So at point number 2, now all the properties are known. Now all the properties are known. Okay. Now let us calculate work done during 1 to 2. Okay. Let us calculate work done during 1 to 2. So work done, try to understand. Work done during 1 to 2. How we used to calculate work done during 1 to 2? Okay. It is nothing but what? It's an adiabatic process, right? It's an adiabatic process. So formula is P1 V1. Try to understand. P1 V1 minus P2 V2 upon gamma minus 1. You can check it. Formula is P1 V1 minus P2 V2 upon gamma minus 1. Or it is also known as MR T1 minus T2 upon gamma minus 1, right? Or it is also known as MCV into T1 minus T2. Okay? MCV into T1 minus T2. I know you. See, P1 V1 is MRT1. P2 V2 it's MRT2. Now R upon gamma minus 1 is C, right? So let's see. In any one of the formula, you put the values, you will get same answer. So let us put in the last formula only, right? So W122 is given by mass. Mass just now we calculated 0.0052 into CV. Okay, CV it is mentioned in the problem. You can check it. What value of CV it is mentioned in the problem? 10.25. Okay, 10.25 into T1 minus T2. T1 was given in the problem, 290. Right? 290 was given in the problem. Minus T2. T2 we have calculated now. 576.29. 576.29. Okay, so just do this calculation immediately and just let me know the answer which we are getting for W122. Okay, do this calculation, or shall I do that? See, it's simple. Like
Minus 15.25.
how much?
Minus 15.25.
Minus 15.25. Okay, no problem. So minus 15.25, right? And what will be the unit? See, this will be in kg. Kg. This is in kilojoule per kg Kelvin multiplied by Kelvin, right? Kg, kilojoule per kg Kelvin. So kg get cancelled. This is again in Kelvin. Kelvin get cancelled. What is it mean? It's a kilojoule, right? It is in kilojoule. Okay, minus 15.25 kilojoule. So this we have finished for W1 to 2, right? Okay, we have calculated work done during a adiabatic process. See, 2 to 3, 1 to 2, 1 to 2, it's adiabatic. So we have calculated work done during adiabatic process, right? Now let us calculate heat transfer during adiabatic process. So adiabatic process itself says that for adiabatic process, heat transfer is zero. Simple. That is the only meaning of adiabatic process. For adiabatic process, heat transfer is zero. Right? So we have finished with the work transfer and heat transfer for process 1 to 2. This is required. This is required for calculating this work. Okay, because this Q1 2 3 1, it's the addition of Q1 to 2 plus Q2 to 3 plus Q3 to 1. Similarly, W1 2 3 1, it's the addition of W1 to 2 plus W2 to 3 plus W3 to 1. Okay, so for which it is required. Now let us move to point number 2. Let us move now to the point number 2. Again, at point number 2, you can check P2 is known, T2 is known, and V2 is known. So at point number 2, all the properties are known. Okay, now we need to get the properties at point number 3. Okay, at point number 3, right? So see, we need to calculate now pressure at point number 3. Try to understand. We should know now. Okay, I'll just mark it here only. Now we should calculate, okay, pressure at point number 3. We should know volume at point number 3. We should know temperature at point number 3. This should be known, right? These values should be known, right? As I told you, okay, pressure, volume, and temperature at every point should be known. So pressure at point number 3 we need to determine. Volume at point number 3 we need to determine. Similarly, temperature at point number 3 we need to determine. Okay, so see, 2 to 3. Okay, 2 to 3. It is what? It's a constant volume process. See, if I write down the law, P2 V2 is equal to MRT2. Is it okay? See, initially I have written this law for process 1. For process 1, I have written. Now, for point number 1, I have written. Now I have written for point number 2. Okay, so from this, can I write down P2 V2 by T2 is equal to MR, right? Same law. See, this I have written for state number 2. Same law I will write down for state number 3. Okay, I'll just write down that for state number 3. P3 V3 is equal to MR T3. So from this, what I will get is P3 V3 by T3 is equal to P3 V3 by T3 is equal to P3 V3 by T3 is equal to MR, right? So if I equate these two, can I equate this? The right hand sides are equal, so left hand sides will be equal. So P3 V3 P2 V2 by T2 is equal to P3 V3 by T3. Okay, P2 V2 by T2 is equal to P3 V3 by T3. But what happens is during 2 to 3, you can check the volume is constant. Okay, you can check it. Volume at point number 2 and volume at point number 3, they are same. Okay, so what we'll do, we'll cancel this. V2 and V3 gets cancelled. Okay, as V2 is equal to V3. Okay, so what expression we'll get? We'll get P2 by T2 is equal to P3 by T3, right? P3 by T3. Okay, now let's put the values. What is the value of P2? P2. Okay, it is already mentioned in the problem. Is 1000, right? 1000. P2 is 1000 upon T2 we have calculated 576.29 is equal to P3 we are supposed to calculate it. P3 we want, but still again T3 is again unknown. See, P3 and T3 both are unknown. P3 and T3 both are unknown. Single equation, two unknowns. Can we solve? Can anybody guess what to do now?
सर इक्वेशन बना के साइड में रख सकते हैं.
No. Sorry, you just see the screen and you just have some idea what we can put instead of T3. I just put the
T3 is equal to T1.
Exactly, right? Because see, 3 to 1 it's isothermal. So here only we are written, na? Temperature at point number 3 is equal to temperature at point number 1, right? So see, I'll just write down temperature at point number 3 is equal to temperature at point number 1. And what is that? 290. Okay. Here I'll just write down T3 is equal to T1 because 3 to 1 is isothermal. So from that, can we get P3? Just let me know what is the value of P3, pressure at point number 3. Do it.
503.21.
503.21. Okay, and see, this is a pressure. This is pressure. Now, unit of P3 will depend upon a unit of P2. Okay, and what is the unit for P2? It's a kilopascal. Okay? So it will be kilopascal. Okay, so this is the value of pressure what we have got. Pressure at point number 3. Okay, so pressure at point number 3 we know. Okay, see, pressure at point number 3 we know. Now, what is the volume at point number 3? V3. That we should also know, but you can check it. Again, V3 is equal to V2, right? So V3 is equal to V2, and V2 already we have know this value, 0.011 meter cube, right? Yes or no? Okay, volume V3 is equal to V2. Similarly, T3. Okay, just now we have put T3 is equal to T1, and that is equal to 290 Kelvin. 290 Kelvin. Are you able to understand this one or not? Let me.
Yes, sir.
Okay, now see, as like 1 to 2, we need to also calculate work done and heat transfer for 2 to 3, right? 2 to 3 we need to repeat. For 2 to 3 we need to do. So see, work transfer during 2 to 3. 2 to 3 it's a constant volume process, right? It's a constant volume process. 2 to 3 it is nothing but a constant volume process. So for constant volume process, how we should calculate work done? Okay, for constant volume process. Okay, so see, we need to calculate work done during 2 to 3. Now see, whenever it's a constant volume, obviously work done is 0. See, work done is 0 for constant volume. Try to understand. You can refer the table which I made. For constant volume process, work done is 0. Because work done is basically the area below the process. So below the process 2 to 3, are you getting any area? No, you are getting a single point. 2 to 3, it's a process. And if you calculate the area below the process on PV diagram, it will give you the work, right? So below the process 2 to 3, okay, so from 2 to 3, it is nothing but a point. It's a line. So when you see it from the top view, it's a point. So you don't have any area. So work done is 0. Now let us calculate heat transfer during 2 to 3. See, for this, I have already derived, we have already taken the derivation for this, why it is 0. Okay, I also summarized it in the form of one table. That also you can go through. Okay. Now let us calculate what is the heat transfer during 2 to 3. Let us calculate now. Okay, what is heat transfer during 2 to 3? Okay, let's do that. Let us calculate heat transfer during 2 to 3. Okay, now see the process. If you just see this process, the process it is nothing but a constant volume process. Just a minute. You can see the 2 to 3, it's a constant volume process. So if a constant volume, the formula is mCV. See, the process is it is constant volume. So formula is M into CV into final temperature minus initial temperature. Try to understand. The process is constant volume. So formula is mCV. If it is constant pressure, the formula is mCP into what? Final temperature minus initial temperature. So T3 minus T2, right? So let us put these values. Mass we already know. 0.0052. CV value of CV it is given in the problem 10.25 into T3 minus T2. What is T3? 576.92 minus T2. T2 we have see T3 sorry. T3 is 290. I'll just write down here. T3 is 290 minus T2. T2 is 576.92. Okay, so just do this calculation and let me know what done during 2 to 3. Okay, this is T3, that is 290 minus T2. Just do this and let me know what value we are getting.
Minus 15.29.
Minus 15.29. Okay, what will be the unit? Obviously, it will be in kilojoule. See, this is in kg. This is in kilojoule per kg Kelvin multiplied by Kelvin. So kg get cancelled, Kelvin get cancelled. The remaining is kilojoule. So see, work done we have calculated for 2 to 3. Heat transfer also we have calculated for 2 to 3. Right? Okay. Now see, now we need to repeat the same procedure for 3 to 1. Again, for 3 to 1, all the properties at point number 3 are known. All the properties at point number 1 are known. Okay. So we just need to calculate the work transfer and heat transfer. Let's do that. Okay. So let us calculate first work transfer during 3 to 1. Try to understand. Huh? Work done during 3 to 1. What is the work done during 3 to 1? See, this is an isothermal process. 3 to 1 is an isothermal process. So for isothermal process, work done is given by, if you just refer the formula, C into log to the base E, final volume upon initial volume. Okay. So this is V1 by V3. Okay. V1 by V3. You can see it. Okay. You can, if you just go through the previous lectures, you'll be in a position to understand it. Okay. So are you able to understand this formula? Let me know. Are you able to understand the formula? Is it okay with the formula or not? See, I'll just browse this table. See, it's an isothermal process. See, this is nothing but an isothermal process. See, this is for isothermal process. So for isothermal process, how will you calculate work done? It is C into log E V2 by V1 because process is 1 to 2. 1 to 2 is process. You can see process is 1 to 2. So final volume by initial volume. Okay. Same thing I have taken. C into log to the base E. Final volume is V1, initial volume is V3. Okay, so let's do that. Now see, instead of C, see, what is C? C, it is nothing but PV. C is nothing but PV. You can check. C is nothing but PV. So that means it is P3, V3, P3, V3 or P1, V1. So instead of C, you can put P3, V3, okay, or you can put P1, V1. P3, V3 is MRT3 and P1, V1 is MRT1. See, try to understand because T3 and T1 they are same, so you'll get same value. Nah? T3 and T1 they are same. You can check it. So you'll get whether you put MRT3 or you put MRT1, you will get same answer because T3 and T1 they are same. Similarly, see what is C? What is C? It is nothing but see. This is C, na, right? This is the value of C. So C, instead of C, what we can put? See, instead of C, what we can put? Either we put P3, V3 or P1, V1 because the process is 3 to 1. So you can put P3, V3 or P1, V1. See, P3, V3 is equal to P1, V1. That means product of pressure and volume is constant, right? So that is the thing which is done, right? Now see, instead of V1 by V3, okay, see, all of you, instead of V1 by V3, what we can put is, we can put P3 by P1. Try to understand. I'm giving you many formulas. Because why I've done it? Because see, P3, V3 is equal to P1, V1. Because process is PV is equal to C. The product of pressure and volume is constant. That means what? P3, V3 is equal to P1, V1. That means product of pressure and volume is constant. So if you just take P3 by P1, you will get it as V1 by V3. Okay, P3 by P1 is V1 by V3. That is the only thing which I've done, right? So we can put any formula. Let's say I'll put the last formula, that is MRT3 into C log to the base E. If you need to solve in a calculator, you can solve it as ln of, okay, V1 by V3. Okay, V1 by V3 or P3 by P1. Anything you can put. Anything we can put, right? So let us put V1 by V3. Let's put V1 by V3. You put anything, you will get same answer. Mass is 0.0052. R is value we are calculated as 4. R is 4 into T3 into T3. T3 is same as T1. You can check it. T3 is same as T1. Is 290 into ln of V1 by V3. Okay, V1, it is mentioned in the problem 0.060 and Okay, V3 we have calculated as 0.011. See, this V1 was given in the problem. You can check it. V1 was given, and V3 we have calculated already. V3 0.011. Okay, so let me know how much we're getting. How much we're getting? Do this. Do this thing immediately. What we're getting? How much we're getting? Answer. Can anybody know?
Sir, ln is log, na?
See, ln is a natural. See, ln. Otherwise, you can use log e. Okay, either way you can do it. See, ln. You can see this term ln. I'll show you 0.0052 into 4 into 290 into, you can see ln of 0.060 upon 0.011. Okay, so this you should calculate. So how much it is coming? 10 point something, 10.23, 10.23 kilos. Is it okay? Yes or no? So this is what we got. Now let us calculate heat transfer. Heat transfer during 3 to 1 again. Okay, see, this is the diagram. 3 to 1. We have calculated work done. Work done we have calculated. Similarly, we need to calculate heat transfer. Heat transfer during 3 to 1. Heat transfer during 3 to 1. But see, the process is isothermal. So heat transfer is directly equal to work transfer. Okay, you can check it. For isothermal process, heat transfer is equal to work transfer, right? And work transfer we already calculated. So that is nothing but 10.23 kilojoule. Is it okay? Let me know. Is it okay or not? Right? Now let us calculate work done during 1, 2, 3, 1. Right? We need to calculate this. See, work done during 1, 2, 3, 1. Okay, so work done during 1, 2, 3, 1. It is the addition of W during 1 to 2 plus W during 2 to 3 plus W during 3 to 1. So let's put the values. Okay, so W during 1 to 2, let's put that value. W during 1 to 2, it is minus 15.25 plus during 2 to 3 is 0. W during 2 to 3 is 0. Okay, plus W during 3 to 1, this value, right? 10.23. Okay, so you'll get some value. Similarly, calculate heat transfer during 1, 2, 3, 1. So heat transfer during 1, 2, 3, 1, it's the addition of heat transfer during 1 to 2 plus 2 to 3 plus 3 to 1. Okay, so heat transfer during 1 to 2, let's see that. Heat transfer during 1 to 2, 0. Okay, plus heat transfer during 2 to 3, it's minus 15.29 plus heat transfer during 3 to 1, you can check it, 10.23. So let me know what answer we're getting. Let me know this value, how much we're getting.
Minus 5.02.
Minus 5.02 kilojoule. This is again minus 5.02 kilojoule. Okay. Now see, everything you have solved. See, everything now you have solved. But how you understand that whatever the problem you have solved is correct? That you should understand. How to check it? See, it's a cycle. It's a cycle. 1, 2, 3, 1. It's a cycle. So for a cycle, heat transfer is equal to work transfer. Say so no? In a case, it's a cycle. So what is that first law says? If it is cycle, so heat transfer is equal to work transfer. So see, you can check, same answer we got. Work done is minus 5.02 and heat transfer is again minus 5.02. So we have got same values for work transfer and heat transfer for a cycle. That means whatever the problem that we have solved, it's correct. Is it okay? Is it okay?
Yes, sir.
Is there any problem? Is there any problem or not? Is there any problem? Is there any problem you're facing? Are you facing any problem in this one? In this numerical which you are taken?
No, sir.
Okay, so today we will stop this session. We will conclude this session. And in the next session, we will try to solve one more problem, followed by the first law of thermodynamics for an open system. That is nothing but a steady flow energy equation. Okay, so I'll just put the attendance link in the chat box. All of you can sign and then you can leave.